Good afternoon, Innovfest. Okay, this sounds like it's on. Okay, so I would like to start this afternoon by taking a poll. Who here has heard of quantum computing? Okay, not bad. I'm an experimental physicist, and I've been working for IBM in the field of quantum computing at our flagship research facility outside New York City. And that's about the best response I've ever seen, so give yourself a pat on the back. Many of you know that, maybe you've heard that quantum is the kinds of computing of the future. But I'm here to tell you a little bit about why that's the case. So in order to do that, I like to take a step back and consider how it compares to classical computing. So classical computers, or that's what physicists call it, conventional computers, they often have, they've been doing some great things, solving vital problems, such as putting men on the moon since the 1960s, doubling in performance every year and a half due to Moore's law. And now they're part of the internet that's connected in our mobile phones, and they're leading to wonderful developments in artificial intelligence and all of the kinds of things you've heard my fellow Innovfest speakers talk about today. But what we don't talk about is there's certain kinds of problems that classical computers can't do a good job with, and they never will do a good job with. I saw a lot of people outside earlier having a tea or coffee. I know I had a couple cups. Well, it turns out that a relatively simple molecule of caffeine inside those cups, you cannot simulate that with any classical computer. In fact, you'll never be able to simulate the energetics, the structure, how that caffeine molecule interacts with your system, how it keeps you stimulated through all of these talks at Innovfest. You'll never be able to simulate that with a classical computer. And why is that? It's because certain kinds of problems, for every atom in a molecule, or every electron in a molecule you add, you essentially double the problem size for a classical computer. The scaling just doesn't work out. And so Nobel Prize-winning physicist Richard Feynman realized this when he said in 1981 that nature isn't classical. So if you want to have any hope of ever simulating what larger sized molecules will do, you'll need to have a computer that obeys quantum physics. And that kind of computer is what we call a quantum computer. So by that time, he realized that, excuse me. By that time, he realized that the only way that these problems would be solved is with a quantum computer. And the next thing that he noticed was it's actually a wonderful problem because it doesn't look so easy. And I've had the pleasure of working for IBM for 6 years in quantum computing, and I can agree with you on that. It is not easy. But I'm here to tell you today that after a lot of effort, we are finally able to bring quantum computing to you, to everyone, the public, for free, on the cloud. And that's what I want to talk about today. But first, I want to go over a little bit more about quantum computing and how it differs from classical computing. So, about the same time where Richard Feynman was thinking about how we could build a quantum computer to study nature, other scientists at IBM were studying the physics of information. And it turns out that classical computing is irreversible. And in fact, there's certain thermodynamic laws that must be followed, such as you must have the loss of energy, the entropy of the system must increase in any kind of classical information processing system. And these systems could be such things as storing a 0 or 1 inside the on-off state of a switch, inside the flow of current of a transistor, or inside the polarity of a magnet in a hard disk drive. This might be contrary to what you're usually thinking, because a lot of times we think about information in the abstract. You think about bits, strings of bits of zeros and ones. But what these IBM scientists discovered is that the information is intimately attached to the physical object that it's stored and manipulated in. So the next thing they realized was, if you wanted to have less energy loss, you could make an irreversible computer, but it would have to be built of something that obeys quantum mechanics. So what happens then if you were to store your zeros and ones, your information, inside of a system that obeyed quantum physics instead of classical physics? This could be like the ground or excited state of an atom, the up or down of the spin of an electron, or the small oscillating electrical current inside a superconducting circuit. So any of these things Instead of obeying classical physics, they obey quantum physics. And that means you can do new styles of computing with them. And this opens up the possibility of computation. So what are the kinds of things that make classical computers special? Well, in a lot of ways, you can think about classical computing and quantum computing as similar, as in kind of circuit gate-based models. But the fundamental difference is that the quantum bits, which we call qubits, obey quantum physics. And in particular, while a classical bit can only be in the state of 0 or 1, a quantum bit can be in a combination of 0 and 1. This is a principle of superposition. There's a second part whereby qubits can be entangled with each other such that you can't describe one qubit without expressing all of them together. They're impossible to describe on their own. This is known as entanglement. Qubits can feature correlations between each other that have no classical physics analog. Their correlations are too strong to explain using classical physics. So what this does is it opens up a computational space that is so much larger than that of classical computing. So that if you were to add a quantum bit to a system, say you add one single bit, then you've doubled the processor of the quantum computer because the growth of that space is exponential. Any kind of quantum algorithm that shows any advantage over classical algorithm is going to utilize this extraordinarily large computational space to do the computing. And this brings me to a point I want to emphasize, is that quantum computing is not about making computers smaller, and it's not about making Moore's law extend into the future. This is about a fundamentally different way of doing computing. And the way you have to think about the computing is completely different from the way you're used to. So how do we actually make these kinds of systems? Well, at IBM, we like to make our computers out of things called superconducting qubits. And the reason we do this, it has an advantage, and that's that the fabrication of these processors is very similar to that of classical processors. They're planar, they exist on silicon, and to my left, on the left here, is a 5-qubit quantum device we've made at IBM. So the qubits themselves are consisting of electrical current oscillations that exist inside each one of these 5 squares right here. And each one of these 5 squares is connected to each other and the outside world by these squiggles, which are actually microwave resonators. So what you might not know, or what you might know, is that these superconductors need to be cooled to a very, very low temperature. In fact, lower than their superconducting temperature, even colder than that, because they're very, very sensitive to noise. So we need to put them in something called a dilution refrigerator, which is this structure, the shiny structure you see on your right. This dilution refrigerator is what allows us to get the quantum devices very cold and operate them in a cold environment while it just sits inside of a normal room temperature lab. Each one of these 4 plates, when in operation, is thermally isolated from each other so that each one of them can sit at a different temperature. This refrigerator relies a classical refrigerator to cool that first plate on the top there down to a temperature of 3 Kelvin. That's 3 degrees above absolute zero, and that's achieved with a classical refrigeration cycle using helium. That is approximately the temperature of outer space right there, and that's just the first cooling part. The next 3 stages are cooled by the exotic quantum properties of 2 different isotopes of helium. Using these exotic isotopes of helium, we're able to get this lowest plate down to a temperature of 10 millikelvin. That is 1/100th of a degree above zero, above absolute zero. And this is where we place our qubits because they're so sensitive. So everything in this fridge right here is either to cool the qubits or to shield the qubits from radiation or to route microwave signals to and from the qubits. That's its entire function, although it does look very pretty as well. Now, throughout history, most people who've ever wanted to use a quantum computer had to construct them and maintain them by themselves. Well, we at IBM have made a lot of progress to the point where we've been able to successfully engineer a quantum computer that's stable enough to operate on the cloud. This computer is controlled by an external classical computer to calibrate it twice a day, but otherwise it's free for users to run for the rest of the day to run quantum algorithms on. Now, it's a very noisy system right now, but one of the reasons why we introduced this system on the cloud is for purposes of education. So we can train the coders of the future, like you, how to think quantum. So what has the reception to this been? Well, since we released the IBM Quantum Experience about 3 years ago, we've had over 16.5 million executions from all 7 continents. Yes, we have had executions from Antarctica, and we have about 140,000 users. One of the other reasons why we put the quantum computer on the cloud is that, I don't know if you believe this, but most quantum researchers do not even have access to a quantum computer. So we let them use ours. We let them use our quantum hardware, and as a result of using that quantum hardware, they were able to publish 170 scientifically peer-reviewed papers that were external to IBM. So they've done a very good job by us offering them this hardware. At the same time, as we've gone along, we've introduced an open source toolkit for the control of quantum computers, which we call QISKit, or the Quantum Information Science Toolkit. You can download this on GitHub, and in fact, it's had over 1,700 forks and over 4,000 likes. So QISKit, not just besides controlling a quantum computer, it also includes algorithms for class platform applications. It includes access to high-performance simulators with configure error models to help us study the errors in quantum computers. And it also includes error mitigation techniques for the understanding and mitigation of errors in these quantum superconducting circuits. We also have tutorials that go along with QISKit, and these tutorials allow you, the user, to go home and start programming any kind of quantum experiment, from measuring the coherence time of the qubits to using quantum-enhanced feature spaces for machine learning. That last machine learning tutorial, by the way, that was just released as a publication from IBM 3 months ago. So we take our capabilities and we put them as part of QISKit as soon as we can. So it's important you check back often. In addition to that, we've started the IBM Q Network. And the IBM Q Network is a community of Fortune 500 companies, of startup companies, of academic institutions, and research labs. We are committed to accelerating the discovery, we are committed to accelerating the progress of building quantum computers, and to that end, we're partnering with industry, and we're fostering the development of an ecosystem. We realize that we can't build this technology by ourselves, and must look to the essential stake of all the stakeholders and innovators out there to do that with us. So to the point, we're collaborating with the best, most advanced research and academic labs in the world to help further the technology of quantum computing. We're partnering with industry thought leaders on developing near-term, first-time commercial use cases for quantum computers. We're also growing, educating, and developing the future of quantum computing by expanding the ecosystem of users, coders, software developers that are essential to the success, their adoption is essential to the success of our platform of quantum technology. So I should say to that end, right now we have a lot of interns going around IBM. We're educating them from both the undergraduate and graduate levels, and we're working on projects with academia as partners in this pursuit. Just 2 weeks ago, we added 16 African universities to our IBM Q network. And this year, we've started camps, QISKit camps, which are hackathons and boot camps for learning QISKit and for developers and coders and physicists and the community to learn how to use our systems and learn about quantum in general. And these have been very successful. I was at the first one in Vermont, and there's since been one in Madrid. And later this year, there are QISKit camps scheduled for Tokyo, Zurich, and South Africa. And who knows, maybe one will be coming to Singapore soon. So I thank you for your time, and I look forward to building a quantum community with you. Thank you.